nearly 30 years. But this paying tribute to my former supervisor. I shall leave the more informal stuff maybe to Wednesday night. So I was Samson's PhD student from 1985 to 88 at Imperial College. While I was writing my thesis on the lazy lambda calculus, Samson was completing his on domain theory in logical form. Samson submitted his thesis in 1987, a year before I did. When I first saw his PhD thesis, it got me really worried. His thesis has 3 parts. Each part was more substantial than my PhD thesis was going to be. Even worse, his external examiner was going to be my external examiner. So I thought there was no way I was going to pass unless he was awarded 3 in the end. I refer to Samson's work on domain theory in logical form, which is a brilliant research program. I think it illustrates very well the power of a semantic framework if it is set up properly. My own work has evolved from semantics to questions of a more algorithmic nature. What I plan to do today is to introduce a semantic framework which is motivated by problems in higher order algorithmic analyses, and more precisely higher order model checking. So what is higher order model checking? So this is as coined by Naoki Kobayashi. Higher order model checking is the model checking of infinite trees generated by recursion schemes for the formal analyses of higher order computation. So it is known that the hierarchy of infinite trees that are generated by higher order recursion schemes have very rich algorithmic properties. Higher order recursion schemes are really just simply typed lambda calculus augmented with full recursion and generated from uninterpreted first order symbols. So it is known that for every n, the new calculus model checking problem for infinite trees generated by order n recursion schemes is decidable, and the complexity is horrendous. It is n x time complete. N is the order, the type theoretic order of the recursion scheme. That's tau of exponentials of depth n. So it follows that these trees have decidable monadic second order theories. And the proof was by game semantics. A few years later, another proof was known. And this was by a completely different method. It was a proof using intersection types. The idea was to show that one can reduce the model checking problem, model checking against for the new calculus formulas, to one of type inference, intersection type inference. Now, since then, 2 other proofs have been published. Today I want to concentrate on 2 of the approaches, one based on game semantics, and the other on intersection types. I'd like to understand the connections between the 2 and whether it is possible to give a unified should mention that both these approaches have given rise to practical algorithms for model checking higher order programs. Now, because of the extreme hyper-exponential complexity, there is no reason to expect that feasible implementations are possible. Except, of course, that the worst-case complexity is only hit by pathological examples, and not by the kind of programs that humans write. Concurrently with developments in the foundations of high-order model checking, a lot of work has happened in the practical implementation of algorithms. So Naoki Kobayashi has pioneered the implementation of these algorithms. There has been a significant advance recently. My student, Stephen Ramsey, using a number of ideas, including intersection types, abstraction refinement, and both success as well as failure types or acceptance and rejection types, has constructed a tool that seems to me to be state of the art. It is empirically linear time in the size of the program, and you can check more than 10,000 rules in a few tenths of a second. I think this is significant because it means that it is now possible to check whole Haskell libraries in a few tenths of a second. So this sets the scene of what I want to talk about. I want to find a semantic framework that relates the game semantic argument and the intersection type. So a brief outline of my talk. I'm going to introduce the intersection types that are of interest to us. These are intersection types that refine the usual simple types. And then I'll introduce a two-level game semantics of these intersection types. Next, I will discuss how one can measure, how one can calibrate the goodness and fit of this model in the form of the substitution theorem, and then I'll discuss applications. So intersection types has a long history. It was, I believe, introduced by Poe, Desartney, Adam Drakenhell to construct filter models for untyped lambda calculus. Recall that intersection types are highly expressive. As evidence, first, this is a folklore result. It is known that the lambda term, untyped lambda term, is beta strongly normalizing if and only if it is intersection typable. It is also known that the type inhabitation problem, that is to say, given an intersection type, is there a term that has that type, is undecidable. It is already undecidable at rank 3. Now, the intersection types that are of interest to us are those that live in the hierarchy of simple types, or those that refine simple types. So, to avoid confusion, when I say types, I mean intersection types, and I shall try to be consistent. Instead of saying simple types, I shall call them types. So, I will read this expression, this relation, theta double colon kappa, as meaning the intersection type theta refines the simple type or kind kappa. So this relation is defined as follows. We fix a set Q of base types, if you like. So Q here is chosen deliberately to be suggestive of a set of automaton states. Suppose we have an index set I. Suppose every theta sub I refines kappa, and theta refines kappa prime. Then we can form an arrow type that refines kappa arrows kappa. The typing rules for the intersection type system is all very standard. One for variable, one for abstraction, and one for application. The thing to note is here, for abstraction, suppose X has this intersection type, and here the assumption is that gamma does not contain any type bindings for X. Then we can form an abstraction which has this arrow. So all this is entirely straightforward. What I'd like to do next is to examine the relationship between the intersection type system and the well-known simply type system with product. Okay. So let's look at the product type in the standard simply type system. Well, the product introduction rule is witnessed by pairing, and the elimination rules are witnessed by projections. Now let's compare them with the corresponding introduction and elimination rules in the intersection system. Note that the witnessing terms are very simple, both for the introduction as well as the elimination rules. So these two sets of rules are similar, but there are important differences. Well, let's delve a bit deeper. We want to understand the relationship between a derivation in the intersection type system and derivations in the product type system. The first observation is that there is actually a very simple, indeed direct transformation from an intersection type derivation to a product type derivation. Well, take this derivation in the intersection type system. To transform it, the first thing we do is, well, just replace all intersections by product. Secondly, well, we have to make sure that we have appropriate witnessing terms. So structurally, it is a very simple transformation. But what about the other direction? Well, it turns out that there are certainly some product derivations that have no corresponding derivations in the intersection system. Here is a simple example. Take this type sequence. It is derivable in the product system, but the corresponding typing sequence in the intersection system is not inhabited by any term. So, a couple of questions. We want to use the product derivations to model the intersection derivations. Why? Because we understand this well. It is more basic. Secondly, how does one constrain the witnessing terms in the product derivations so that they correspond to the intersection derivations? Well, here is one idea. A product derivation has a corresponding intersection derivation only if for every pairing construct in the derivation, the two component terms must be coherent in a certain way. So our investigation suggests the following reading. To model an intersection derivation using a product derivation, we decompose the intersection derivation into three components. The upper structure is just an ordinary product derivation. The lower structure is a lambda term, and there is a forgetful map on nodes from the upper to lower structure. So this motivates our construction of the two-level game semantics. First, a bit of recap of quite standard game semantics. We first fix a set of colors, set Q of colors. We should think of elements of Q as three-automaton states or base types. Now, a Q-colored arena, or tuple, is just an ordinary arena in game semantics. N sub A is the underlying set of moves. Turn style sub A is the enabling relation. Lambda sub A is the map that tells whether a move is owned by P or by O, either of the two players. And the new thing is this coloring map, which maps moves to colors. What are our strategies? Well, in addition to determinacy, we require P strategies to satisfy the color reflection axiom. That is to say, only opponent, only O, can change color. Now, this is quite standard. The category whose objects are Q-colored arenas and whose maps are innocent strategies is enclosed. Well, next we move on to a semantic situation in which we can model intersection type derivation. So what is a two-level arena? Well, a two-level arena has two structures, an upper level structure and a lower level structure mediated by a forgetful map. So, more precisely, the two-level arena, which is based on Q, the set of colors, is a triple. A, the upper level structure, is just a Q-colored arena. K, the lower level structure, it is just an ordinary arena, which is the base of A. And U is a map, mapping moves of the upper arena to moves of the lower arena. We require this map to preserve a few things. First, it must preserve player-opponent polarity. Secondly, it must preserve the enabling relation. And thirdly, it must preserve initial moves. Now, U, the mediating forgetful map, is important. Suppose we have a play of the upper arena. U, thanks to these axioms, applied to M, gives us a justified sequence, which is a play of the lower arena. Okay. Well, we have seen what two-level arenas are. What are the strategies of this two-level world? Take a two-level arena. An innocent strategy of this two-level arena is a pair of innocent strategies. upper strategy is a strategy of A, and the lower strategy is a strategy of K, the lower arena. Such that the image of U, such that every play of the upper arena under U is a play of the lower arena. Well, now we have the objects, which are two-level arenas, and the arenas, and the maps are pairs of strategies, one for the upper, the other for the lower.
Can I ask, is this some kind of gluing construction?
Well, there is a characterization of this setting, which I will talk about.
And you formally see it as gluing, that's what I'm asking. It looks very much like gluing.
Well, it's a kind of vibration. I'm jumping the gun. So in this category, one can do the standard sort of things. One can build product arenas. What we do is just to form products of the upper and the lower components. We can build function space arena. We do the same thing. We form function space in the upper and the lower world respectively. We can build intersection arenas. For that, we have to make sure that the two-level arenas share the same base. And the arena that is constructed is indeed the pullback of these two maps. Okay, so it's not too difficult to show that the category whose objects are two-level arenas and whose maps are innocent strategies form a Cartesian closed category. We have built a semantic structure. Does it serve our purpose? Some very natural questions follow. How does the upper level computation relate to the lower level computation? Indeed, how well does the two-level game semantics model intersection types? Well, the answer lies in what we call a de-substitution theorem. I explain why we think it's reasonable to call it a de-substitution theorem. But before that, let me just explain informally what this theorem is about. Intuitively, it says that the two levels are they fit together very tightly in the following sense. Every lower level computation is canonically and closely tracked by a higher level computation that lies over it. So a bit more precisely, the de-substitution theorem says that given an upper level map F, for every factorization of its projection in the lower category, there is a canonical factorization of F that lies over it. Now,
when you say canonical, do you mean that a choice can be made and we can call it canonical, or there is something that physically is a theme?
There is a obvious factorization, in that sense canonical. The canonical also means a couple of things which I'll say a bit more. Now, why desubstitution? Well, in categorical type theory, we know that composition of maps corresponds to substitution. Factorization is the reverse of composition. It is decomposition, if you like, hence desubstitution. So here is a more precise statement of the theorem. So, well, let P be the obvious projection functor. So given a map of the two-level world, recall that a map is an innocent strategy. It is a pair of innocent strategies. The upper strategy is for the upper world and the lower strategy for the lower world. The projection simply projects it to what happens in the lower. So the theorem says that for every map in the upper world, and for every factorization of its projection in the lower world, there is a factorization of the original map in the upper world that lies over this factorization. And the factorization is canonical in the sense that there is a very natural arena A, and for every other triple that satisfies this commuting diagram, there are canonical injections from A. So it turns out that this desubstitution theorem, or rather the shape of the assertion, is a variant of the Conduce vibration, which was introduced by Zhu in 1964 in characterizing functors between small categories that are exponential, which everyone knows well. But there is a difference here in the Conduce definition. The factorization is unique up to equivalence. In our situation, it is not unique up to equivalence, nor is it unique on the nose, but it is canonical in the sense that I just described. So let me move on. So I think of this result as telling us something about the structure, and as I hope we will see, the robustness of this structure. So just to conclude this part, we have built this two-level semantic framework. We can interpret the intersection type system in this two-level game semantics in pretty much the obvious way. And this model turns out to be very tight-fitting in the sense that it satisfies a definability result. To explain that result, let us say that an innocent strategy sigma is winning, just in case it is compact. That is to say, the domain of the generating view function is finite, and it is total, in the sense that player P is always able to respond. So the definability theorem says that let F be a winning strategy. The domain and codomain being the interpretations of a type sequence. Then there is a intersection type derivation that denotes. So we now move on to the last. How am I doing for time?
Time is not a concern.
I don't say that very often.
Beyond my allotted time, that's not fair. And he may bore you.
The chairman is completely.
So some algorithmic applications. Well, it turns out that the substitution theorem has a number of rather pleasing applications. They can be applied, well, I'll explain three. So these are results that are of an algorithmic nature, and it's pleasing to be able to use a semantic theorem to prove it. For the first one can use the substitution theorem to give a correctness proof of Kobayashi's theorem. So he showed that model checking of recursion schemes can be reduced to type checking for the trivial automatons. A second application concerns a certain minimality property of another model checking algorithm which is based on game semantics. The third application has to do with one of the many algorithms for model checking high-order recursion schemes introduced by Kobayashi. This one is inspired by game semantics. And typically, the completeness is the difficult direction, and it can be used to prove that. But what I'd like to talk about is an application of the substitution theorem to higher order matching. Now, I will not be speaking much of higher order matching proper, but an equivalent decision problem, the interpolation problem. So what is an interpolation equation? Well, this is the equation. You have an unknown x applied to u, and on the right hand side of the equation you have v. U and v are closed terms, lambda terms, in beta eta long normal form. Now u and v may contain constants. So these are constants which may be higher type constants. And gamma is an environment of kind bindings of constants. Okay? So given such an equation, can one solve for x? This is the interpolation problem, and it is known that this is, as a decision problem, is equivalent to higher order matching. Colin Sterling in 2009 was the first to show that higher order matching equivalent interpolation is decided. Now, I want to talk about a number of characterizations of the interpolation decision problem. The first one is by game semantics, as introduced by Colin Sterling. The second one is in terms of a new kind of tree automata called dependency tree automata. Dependency here refers to the binding links between those. And it turns out that there is a third characterization of the interpolation problem, and it is in terms of intersection types. Precisely, the decision problem interpolation reduces to the decision problem type interpretation, which asks, given an intersection type, is there a term that has that type? Now, so I want to apply the substitution theorem to show this. The reduction of interpolation to type inhabitation. Well, first, a lemma. We fix an interpolation equation. Let us assume that the closed term on the right-hand side, v, is of ground type, and the term on the left-hand side, which is the operand of the unknown x, has, let us say, a higher type couple. The lemma says that there is an intersection type sequence that characterizes a given lambda term in beta eta normal form, in the sense that given a simply typed term t, t inhabits this type sequence if and only if s and t are beta eta equivalent. Okay. So here's an example. Okay. So take this lambda term, f and a are constants. We want to find a type sequence, intersection type sequence, that characterizes the equivalence class of this term. So here is a type environment. So the idea is for every ground type subterm of S, we introduce a ground type. So there is a ground type for A ground type for FA, and a ground type for F applied to FA. So here is a typing sequence that characterizes terms that are beta eta equivalent. So now we can complete the argument by applying the substitution theorem. So we want to show that a lambda term is a solution of the interpolation equation x applied to u is equal to v if and only if a certain type sequence is inhabitant. How is this type sequence obtained? Well, recall that given a term in beta eta norm form, we can construct t sub v and delta sub v. This sequence characterizes it. So we use u and v and form this environment and this intersection type. Now, the difficult direction is from left to right. That's to say, suppose we have a solution. How can we show that it inhabits this type? And to do that, well, we just appeal to this substitution here. So, it's time for me to conclude. So we have seen a two-level game semantic framework that models intersection types. This is an example, but there are many other instances which suggest very strongly that game semantics and intersection types and other semantic methods are very useful tools for higher order algorithmics. Secondly, the two-level game semantics of intersection type, as we have seen, satisfies the definability theorem. It is accurate, and its robustness is indicated by the substitution theorem, which has several applications. So this is a first step in what we hope is a program that will eventually show us how we can compose parity games. parity games, as we know, is equivalent to model new calculus, and model checking is, in general, most non-compositional. So our plan is to extend this framework to talk about not just trivial automata, but automata with priorities. So these are alternating parity tree automata equivalent to the model new calculus. Our aim is to obtain a Cartesian closed category of parity games. That, I think, would sum up what we mean by composing games in a higher order setting succinctly.
Thank you. We have time for questions. Samson?
So if I understood, the reduction you gave is, I mean, it's to an undecidable problem. Could you imagine using the methods you described to get a new proof of the interpolation or higher order matching theorems?
There is no hope. There is no hope. We don't know. It would be nice to be able to explain or perhaps simplify.
Yeah, it's a beautiful framework.
Any other questions? Yes, Paul?
Going back to this canonical lifting of a factorization, did I hear you right? Did you say that it's initial lifting? So you've got a factorization downstairs, you've got a category of possible factorization upstairs, and your canonical one is initial in that category? Is that what you said?
Well, I didn't quite say initial, but but this is the precise statement. So there is a canonical factorization in the sense that for every triple that satisfies this constraint, there is a map from the moves of A to the moves of A prime, that satisfies this one.
Okay, but it's not unique. So that
You mean
one
you mean the phi?
Yeah, phi is not unique.
Phi is unique.
Okay. That sounds like it could be an initiality statement.
It could be, but it's so this proof is highly technical. It involves using the interaction sequences that live in the lower world to construct T-view, if you like, of the upper world. This may not be the best formulation. To tweak this, one has to go back to the argument